Hello, everyone, and welcome to this FLOW seminar. FLOW stands for Federated Learning One World seminar. And yeah, we have regular talks that you can attend live, but they will also be put on YouTube, so for you to watch later. And this week, it's an honor to have Geovani Rizk here as a guest. He did his PhD in Paris on a bit different topic on online learning and bandit problems. And now he joined EPFL as a postdoc and is working on robustness in federated learning, in particular on batch norm for federated training. And I think many of us that have tried to apply our algorithms for neural networks realize that batch norm is really a big challenge. And yeah, we are looking forward to your talk where you explain us what we can do. So, welcome, Geovani. Thanks.
Thank you very much, Sebastian. So indeed, today I will talk about a project that we have here at DCL at EPFL with Rachid Guiraoui, Raphaël Pinault from Sorbonne Université, John Stefan from EPFL, and François Tajani from INRIA. So the topic of this project is overcoming the challenges of batch normalization in federated learning. So first of all, let's start with some context and background. You all know this simple and famous example that is, let's try to classify images of cats and dogs. And how do we do it? So in classical centralized machine learning, what we do is we have this dataset S that has some images of cats and dogs and that are labeled. We feed it to a model that can be here a neural net. And given according to the prediction that gives this model, we can compute a certain loss that says how good was the prediction or how bad it was. And so if the loss is high, it means that it was a bad prediction. If it's low, well, we are somehow having a good estimation, a good prediction. And the overall objective is to minimize a certain function L of theta, where theta represent the model parameters, and that is basically the average loss over all the samples that we have in our dataset. So this is the simple task. How do we actually solve that? So most common common approach to minimize this function is to use what we call SGD, or more precisely mini batch gradient descent algorithm, where at each iteration t, we sample a batch of data. So here x1, y1 to xk, yk. X is the input, y is the label. And we compute the gradient given the loss that we had. So the gradient here is the average gradient over the batch that we sampled just before, and we update the model parameter theta, and we do it iteratively. Now, if we sample a batch from a certain data, well, it means that we can use batch normalization. And why do we want to use batch normalization? It is because batch normalization in deep neural networks, convolutional neural networks, stabilizes and accelerates the learning. And let's see what is actually batch normalization before going more like specific into federated learning. So let's consider a class of neural networks of the form like this, where you have different layers phi of 1 to n. So here, theta represents the model parameter, and each function phi represents a layer of the neural net. The batch norm is used to normalize the input of each layer. Okay, so basically, what do we do? At each layer, we have a batch. So the same the batch that you sample. So for the first layer, the batch that you sample from the data. So mu1 to u1 to uk. You have different parameters, which is the momentum, and we will see that after. And just keep in mind that we have what we call running mean and running variance. So what do we do first? We compute the statistics of this batch. So first of all, we compute the mean. U bar, and the variance, sigma hat square. Okay, given those statistics, what we will do is to normalize those data. So basically, removing the mean and dividing by the variance. Here, this epsilon is just for stability issues. And alpha and zeta are here just as learnable parameters, but in this paper, it's not really what is of interest. So just keep in mind that here, what we have is those new data that are normalized given those current statistics, mu bar and sigma hat square. Given those new statistics computed, what we can do is updating the running mean. So the running mean is equal to this coefficient times the old running mean plus beta times the new current mean that we computed, and we have exactly the same for the variance. And those statistics actually are really important at evaluation time. So batch norm is used during forward pass, so during the training. So those normalization computation are have an impact on the gradient when you compute the gradient during the learning, but those running statistics are only used for now at evaluation time, where you don't want to be dependent on the data that you receive at test time. And of course, at the end, sorry, the algorithm just output the normalized version of the vector that you got in input and the running mean and running. So I just explained centralized machine learning, where you have like a simple task to solve, but of course, we are not at the stage of just trying to classify cats and dogs. What we want is also like having to tackle, sorry, more complex problem as like classification of panel signal on the street, or even like a medical application as like detecting early stage disease or whatsoever. So basically here, the problem is that for cats and dogs, it was easy to train a model on a single machine because the model was really small. The data were really simple, and we could learn it in an efficient way on a single machine. Right now, having those kind of application makes us force us to use more machine to distribute actually this task. So because we have more data, we have models that are increasingly growing, and actually for medical applications, for instance, or actually other applications that use sensitive information, we would want to keep this data sovereignty and maybe try to keep the data where it is, and most of the time at the client side. So we need to distribute the learning task. So instead of having just this paradigm, what we have is federated learning, where you have exactly what I showed you just before, but for on different clients that all communicate with a central server. And basically, how does it work? So each client will do exactly the same algorithm that I just showed you, so SGD. Then given the model that it gets, sorry, yeah, I forgot to tell. So in that setting, since each client has like its own loss, what we want is to minimize the average loss over the client. And how do we do it? So how do we learn? Basically, after learning from their side, the client will send their updated model to the central server. The central server will average those models and will send them back to each client that will start learning from this updated model. So here, just to be clear, we do the average because basically, as I said, we want to minimize the average of the losses over the clients, okay? Now, there is a problem when we use batch normalization in federated learning. Why? Because when we use batch normalization in federated learning, each client will normalize its data depending only on the local statistics that it has. What does it mean? It means that each client will sample a batch and will compute the mean and the variance of its batch and only its batch, and will not see the batches of all the other clients, and will normalize depending on that. And this is an issue because what we want in federated learning is exactly trying to do what is done in centralized learning, but just having different clients that do that task. And this is not the case in batch norm in federated learning. And it creates external covariance shifts. And to be more precise and to have like an illustration, let's have a toy example where we have simulate some data from 10 different Gaussians. So in the central setting, when we have those data, the data in a circle, those are the data before normalization. In the central setting, we will compute, as I said, the mean and the variance. Here, the mean is 0, and the variance is somehow approximately equal to 10. So what it will do, it will simply like divide all those values by something around square root of 10, and all the values will be normalized like this. If we use batch norm as it is in federated learning, what it does is basically, so each client will have, if we distribute the data such that each client has just one Gaussian, so each client will have a mean that is not equal to 0, 0, but that is centered in their points, and the variance is equal to 1 in that particular example. So what batch norm in federated learning will do is simply shift all the cloud of points in the middle, and actually you can see that we will lose separability. And this is actually something that we believe is the main issue of batch norm in federated learning, is that the way we use it right now is that makes the data less separable. And this is something we actually wanted to solve in this project. The second problem here is that, okay, we computed the mean value and the variance of the batch. We normalized the data. This is one thing, but we also updated the running mean and running var. And as I said, those values will be used at evaluation time. The problem is that when the server average those values, so the running mean and the running var, it doesn't get exactly what we have in the central setting. Why? So basically, because when you do the average of local variances, it doesn't give you necessarily, and actually in general, it doesn't give you the global variances, and we will see that after. But basically, the consequences of that is that at evaluation time, you have bad performances. So given this problem and given those challenges, we came with our solution that we call Federated Batch Norm, or FBN. And let's start with some insights. So we know that at each iteration, the clients cannot have access to the data of other clients at the same round. Otherwise, it would just have taken all the data, compute the global statistics, and normalize the data properly. So we know that we don't have that. However, what we can try to see is, what if the global statistics of previous round were similar to the one that we have at the current round? So what if global statistics at time t is similar to global statistics at time t-1? If it is the case, well, what we can say is, instead of normalizing the data with the current statistics, so the one that each client cannot have, let's try to normalize the data with the statistics of previous round. So maybe the normalization could be really close to what we would have in the central setting. So the objective here is to save the global statistics of previous round and use them to normalize the data. This is fortunate because we are already saving running statistics, so running mean and running variance, and we send them to the server, which means that at the next round, when the server will give us back the running mean and running variance, we can use them to normalize the next data. The problem that arises here, as I mentioned previously, is that the averaged value of the running statistics differ from the ones observed in centralized setting. Why? As I said, the variance, the average of the variant of the local variance is not equal to the global variance itself. So we will have to modify the way of aggregating the running statistics. So not necessarily just averaging the running statistics, and try to actually unbias them, because right now, for now, we have a biased version of them. And basically, this is what we do with FBN, so Federated Batch Norm. We use an unbiased version of the running statistics. So we aggregate well the variances, and we use them to normalize the data instead of using batch-specific statistics. Now that we have the big picture, let's try to go into the details. So here in what will follow, I will try to do the parallel between federated learning, so what we have in federated learning in terms of statistics, and the statistics that we should have, or what we would have had in the centralized way if we just merge all the batches. So in the federated setting, at a certain iteration t, we have each client I that has a batch of k values, so u1 to uk. For each client, we can compute the local empirical mean, u bar, and its variance, its associated variance. Basically, it's as simple as it is. We just compute the average value of the k vectors, and here the variance of the k vectors. But just keep in mind that it's the local variance here. Okay, we just have the information of each client batches. In the central setting, if we want to merge all those batches together and learn in the central setting, what we would have is the average of all the values that we have in all the batches of the clients. So basically 1 over kn, where n is the number of clients and k the number of samples per batch. And we would have the global variance. And here, as you can see, it depends not on the on each local mean, but on the global mean, mu bar t, which is the global mean that takes all the samples from all the clients. And again, if you do just the average of those values, you will not have in general this global variance. So right now we have the current statistics, so the ones that we have at round t. And what we want to have is the parallel also between the running means that we would have in federated setting and the running mean that we would, and running variance that we would have in central setting. So in federated setting, what we propose here is to have the running mean at round t to be equal to have exactly the same formulation as the one in the standard batch norm, which is this coefficient times the last running mean plus the new update times beta. For the variance here, there is a small difference. Instead of having k over k minus 1, we added this n because what we want is to retrieve this central behavior. And we know that at the end, we don't have k samples. We have to deal with k times n samples. So instead, in order to have this unbiased term, in unbiased variance, we multiply the new variance by this coefficient that includes the number of clients. What do we have in the central setting? Well, we don't have several clients. We just have one machine. So we just have one running mean and running variance to compute, which is basically the last running mean plus the updated one modulo those momentum parameter, and exactly the same for the variance, where you can see that you have kn over kn minus 1, which is here to have the unbiased variance. So here, given those value, what we want is given those local running means computed by the client, we want to see what aggregation we must do to retrieve those global running mean and global running variance computed that would have been computed in the centralized setting. So how do we aggregate them? So we know that doing the average of the means equals the global mean. This is not surprising. This is actually really simple. So there is nothing to do for the average. This is already well done in federated learning in general. When you have batch normalization, you send the running mean to the server. It just does the average, and you get the unbiased version of the global running mean. The problem here is that, as I said, the variance, the global variance that would have been computed in the centralized setting is not equal to the average of the running means, of the local running means of the client. So we need to find another way to retrieve this value, and basically it's actually simple. We just follow the rule, the law of total variance, total variance, and we add this term, this correction term that is basically the variance of the means, and we multiply it by this coefficient just to retrieve exactly the centralized running variance. And by doing that, we actually, in federated learning, retrieve the exact running mean and running variance that we would have in the centralized setting. Now that we have those nice equations, let's try to understand what actually FBN does in a more concrete way. So at for each batch norm component, each client will receive a batch of data, so from mu1 to mu_k. Each client has the same momentum, the number of clients, because it will have to use it to create this coefficient, the numerical stability as we had in the batch norm components, and the running mean and running variance that have been sent by the server. Next, so for each client, what each client should do is first normalize the data, not according to the current statistics of the data. So we don't use any statistics from those mu1i to mu_ki. What we do is we normalize given those previous statistics shared by the server. Then we compute the current statistics of the batches that we have, of the batch that we have. So we have the local mean and local variance of each client. We update the running mean, as I mentioned before, for each client. We update the running variance, and we add this n here to be able to retrieve at the end the right running mean and running variance that we would have in the centralized way. We send them to the server. So the running mean and running var are sent to the server. The server will average the mean, because we know there isn't any issue for the mean. However, for the variance, what the server should do is add this term, and it can add this term because so these values have been sent by the clients. This value, it has to compute it just before to average all the mean. So the server can actually correct and unbias this variance, variance term to retrieve the centralized one. And at the end, the server send back those shared statistics to each client, so they can use it at the next stage. And of course, the whole thing is to normalize the data. So at the end, each client will send these value that are normalized, okay, not with this batch-specific statistics, but with the running mean and running variance. The question is, okay, how does it perform? is it a good approximation or not? So basically, are those values, so mu hat run and sigma hat run, close to what we would have had if we use the global batch specific statistics. So here in the left plot, I just put again the centralized setting, where indeed we normalize well the data, and the data are still linearly separable. What FBN does is actually something really similar. Just keep in mind that FBN works in an iterative way. So indeed, at the beginning, the running mean and running variance of previous round are the one, for instance, at the first step, are the one by default. So indeed, it is not exactly what we would have in the centralized setting, but after some iteration, you converge quite quickly to this result. And we compared ourselves to a method that is called FixBN that also use running statistics. During a first stage, it will just do batch norm as it is. So as we know, and as it doesn't work well, and then it will use the running statistics that it computed, but the one that are biased. And this is why actually we see that here the data are still separable, but we lose the actual benefit of batch normalization. Now that we understood that FBN keeps this separability property, what we wanted to see is what are the performances of FBN in a more complex data set, and we tested it on Cypher10. What we did is to simulate the learning in different kind of heterogeneity setting. When we are in a homogeneous setting, of course, everything works well for everyone. Why? Because when you have batch norm in an homogeneous setting, every client has compute statistics that are the same because they have the same distribution. But the more you go into an heterogeneous setting, the more batch normalization, so the naive one, the one that just used batch norm and send it to the server will just average, will not work at all. This was the problem, the initial problem. You can see that FixBN is somehow improving actually a lot the thing, but still you have a gap between the centralized performance and their performance. And what we were able to show is that when you use FBN, you actually match the centralized performance. So it is exactly the same. It's almost exactly the same thing as just running everything on a single machine. Of course, our method is an approximation, so it's not exactly the same, but it matches the same magnitude of performance. Here you have the training curves. So for basically this case and this case, so the first one is almost extremely heterogeneous, and the second one is extremely heterogeneous, where each client has just one class of the Cypher10 dataset. And as I said, FixBN works in two stages. The first one is doing exactly what batch norm would do, naive batch norm would do, and then it will use the running statistics, but that are biased. And what we do is using directly from the beginning running statistics that are actually well computed, so we retrieve exactly what we would have in the central setting. And you have the same behavior in the extreme heterogeneity setting. So having said that, we first presented a method that indeed matches the performance of what we would have in the central setting, but federated learning in general, so this setting, implies some vulnerabilities. And before exactly talking about batch norm, I will try to explain where those vulnerabilities can come from. So basically, if we go back to this figure where we have different clients and different server, a server, sorry, that communicates with a central server. Sometimes we could have some clients that could crash, for instance, okay, or that can take more time to respond, or that can be hacked, or that can be actually malicious and try to send wrong information to the central server. So basically, when you have that kind of behavior, and actually we can refer to the Byzantine machine learning literature. So when you have that kind of behavior, the actual model that each client will send could be corrupted. So basically here, each client will send its model. So when I talk about model, it can be the model itself, the statistics of the batch norm, or whatsoever. So anything that has a link with the model. It could be also gradient, actually. So each client will send its information. The server doesn't know who actually is malicious or not. So the server will simply average the model and will get a corrupted model, and will send back a corrupted model to all the clients. And this is actually something that we don't want. This is with actually a single client, we know that we are vulnerable to that kind of attacks. So instead of using the average, what we could do is using robust aggregation. So even in the presence of some adversarial clients, I say some because we have a condition on the number of malicious clients, we might be able to have a good model, a model that would still make us learn. And then the server can again send the good models to learn on it for the next step. So we want to do the same for batch norm, because batch norm will send, so each client will send their statistics to the server, and we don't know if some clients could send malicious statistics, and if one client send malicious statistics, we want to know what could happen. And actually we tested that. So here, so the top curve in blue is when FBN is not attacked. You have exactly the same for batch norm. So this is in almost extreme heterogeneous setting. This is in extreme heterogeneity. We know that batch norm is not behaving well because of all the problems we said before. When you don't attack, even batch norm is not behaving well because we have those statistics mismatch. We know that Fed match norm matches exactly what we have in central setting. Now, when we attack either FBN or naive batch norm, we can see that the learning is affected, and actually even FBN has bad performances. Here, BN is still around 20%, which is really bad. And in extreme setting, this behavior is highlighted. However, when you change the average by a robust aggregation, so here what we did is instead of using averages, we use median. And we can see that FBN is exactly matching still the central setting when there isn't any attack. We have it in both cases, so in both heterogeneity setting, whereas batch norm is still bad because of this mixture of batch norm was not as good as the central setting, and also it allowed to attack it actually even simpler. So to conclude, in this for this paper, in this project, what we did is first we presented FBN, that is like a novel method for batch norm in federated learning that actually matches the central behavior. We identified the vulnerabilities of batch normalization in EPFL, and actually this is something that has not been seen in the literature because all the vulnerabilities were focused on the gradients or the models. And we proposed like a robust version of FBN that makes the learning still good. Now, the question that we can ask ourselves is, well, FBN is not using any batch-specific statistics, meaning during the training, during the forward pass, the clients are normalizing the data with old statistics, so not the statistics of the batch they sampled. So why don't we use them even in centralized setting, and why do we need batch-specific statistics in the first place when we do batch norm in centralized setting? I think it's all for me. Thank you very much for your attention.
Okay, thank you very much. Thanks for the talk, and that was very good explained how to implement this and so on. So are there any questions from the audience? So please, you can write in the chat and I can read it off, or you can raise your hand. I think that's the best, and I can unmute you. Or basically you can enable this and everyone can unmute and just ask questions. And okay, maybe before take some time for people to come up with questions. So if you go F1 thing, I think there was a typo on slide 19. You had some X variable, but maybe this was new, or I was confused. So there was
sorry.
so 19.
19. Sorry, you said.
It's for the main formula. So this the
purple
term.
So it is a completely typo. Thank you very much for pointing it out. So it's basically mu U bar and U bar here. Yeah.
Okay.
Thank you. Yeah. It's using actually the average, the local average is here, and the global one.
Yeah. Okay. Yeah, I think that's very interesting formula now. So you can say that. I mean, we know that this first estimation, just taking the average, is biased, but then you can correct it with this additional term. Okay. So there's a question in the chat. So can you explain how to get beta and gamma in the federated learning setting?
So beta. Let me just remove that. So beta.
Maybe this is beta. Yes. Yeah. Sorry.
Yeah. So beta here is. Let me go back to this. Yeah. Beta is the momentum you want to give to batch norm. What does it mean? It means what is the importance of the history of previous round when you want to compute the running mean and running variance. For instance, at the beginning of the training, indeed, I would say beta should be large. Why? Because the parameters and the statistics will change a lot because you're learning. But maybe at the end of the training, you would want to have beta that is really more close to 0 because you are in a stabilized area, and somehow the statistic will not change. How to get them? It's completely a hyperparameter. For now, for instance, if you use PyTorch, it is set to 0.1. It is something that works quite well. We didn't have to change it. But actually, this is an interesting question, because maybe changing beta in our case, because FBN is using the history of previous round, maybe this parameter can actually improve the performances. But since here we already matches the centralized case, we didn't investigate further. But maybe in larger models or something like this, maybe this parameter should be optimized either by just doing a grid search, or maybe try to find a better a closed form to compute it. But for now, it's just grid search, or you take default value that for now was 0.1. For gamma, sorry, what is gamma for you? Because
yeah, I don't know.
I don't remember putting gamma in this presentation, but maybe I'm wrong.
Yeah, maybe it was alpha, but yeah, I don't know. I think you clarified now the beta, and maybe
Yeah.
the person can ask again or clarify. Yeah, so there's another question in the chat, but as mentioned before, please just ask live. Okay, so a question by Satish. He asked on the robust estimation part from the end, where you use the median, and the question is, do you only use the median when you do the aggregation on the server, or do the clients themselves also use the median?
No, so the clients don't use the median. They do exactly what the server asks them to do, which is all the formulas that I show. So it is like averages or updating the running mean and running var. But when the server receives those values, it cannot trust if the server is right or wrong. So it is on the server side that we do this robust aggregation, so the median. And indeed, if we have some extremum, we know that median can be robust to those extremum values. And that's why we do it on the server side. The client side should do what we want in the best case, where we don't have any problems. And it is on the server side that we should be careful and try to aggregate those value in a safe way. And actually we showed results on median, but we did some other experiments on other robust aggregations. But median was actually enough to match the central case, so that's why we showed that.
Thanks. Okay, there's a question by Hyun Ru. I will just ask you to unmute.
Yeah, hi, hello. I'm not sure if my voice is clear or...
Yeah, it is.
Okay, great. Yeah. Thank you very much for a nice presentation. So my question is mainly about about the data heterogeneity. And so I'm wondering, what is the heterogeneity you're talking about? So for example, is it the label heterogeneity or like number of samples? Because I think there are a lot of different ways of heterogeneities in terms of the federated learning settings. So can you explain more in this?
Yeah, indeed, you're right. And actually, it was a choice to not talk about that. I just wanted to have some level of heterogeneity and just have like a big picture of that. But indeed, what we used here is gamma similarity model, which means that this gamma is the portion of similarity that you have between clients, which means that here, 1% of the data is from the same distribution, from a uniform distribution. So each client will have 1% of its data that comes from any of the classes, and 99% of the data actually comes from one class here in this setting. Extreme heterogeneity is one class per client. So it is when gamma is equal to 0. So you have 0% of similarity between clients. What we did also is to use the Dirichlet distribution. I don't know if you're familiar with that, but so instead of having this notion of similarity, what we do is we sample vectors from Dirichlet distribution, and this vector could be sparse depending on the parameter you choose. So you have an alpha parameter. The more alpha is close to 0, the more those vectors are sparse. And basically, those vectors gives you the proportion of class you have per worker. And we did also those experiments that are actually presented in the paper. But here, since gamma similarity and capture also the extreme heterogeneity case where each client has one class and one class only, we choose to present the gamma similarity model. But you have different ones, and it was just a choice for the presentation.
Yeah, thanks. So I think the Dirichlet distribution is more familiar for me. I think it's like a lot of research also use that. And another small question, like, so what's the number of clients you have then? Did I miss
here
in your presentation?
We simulate with 10 clients.
Okay, yeah.
So what we wanted is to capture exactly this extreme heterogeneity case when you have exactly the same number of classes and the number of clients to really have different kind of data per client. So that's why we choose 10.
I see. So yeah, so the extreme heterogeneity just like one class go to one client then. Okay.
Exactly. So one client will just see dogs, the other one will see cars, and etc.
Yeah, and one final question. I will not spend too many time. So, what about the cases in asynchronous federated settings? For example, like if the client updates like synchronously, not at the same time each round, how it will perform, or like how do you see, or is there any already results you get from this kind of cases?
It's a good question. Actually, because we didn't investigate that direction, but it is an interesting one. But my first guess would be that since you're using previous round estimation of the global statistics, I would say that there is a chance that FBN could work. To be honest, we still didn't investigate that, but because you use the history of previous round, okay, you're asynchronous, so maybe you have 1 or 2 rounds, you are 1 or 2 rounds late. But if your statistics do not change too much, then I would guess that the normalization could still work. I think yeah, but it could be really interesting to try.
Yeah, sure. Thank you very much.
Thank you.
Thanks. So there was one question in the chat from Brahim, and he asks about, did you think about this client sampling strategy? You know, that's sometimes used in federated learning where you just activate a subset of the clients. Can you then still estimate the variance, or did you try to test this?
So if you do subsampling, okay, there is two parts. When you don't have any malicious client and when you have malicious clients. When you don't have any malicious clients, well, it works exactly the same, if I'm not mistaken, because if you just subsample some clients in a centralized way, what you would do is just merge those batches sampled by those clients, so the data sampled by those clients, and you would do exactly the same as what I presented. So there is no difference. You would actually retrieve exactly the global statistics that just this subsample set of clients did. So this is exactly the same. I don't think that we would have a difference between what we would do in federated learning or centralized setting. Now, if we talk about the robust part of this talk, so when you subsample clients, well, the problem is that I said previously, we have a condition on the number of malicious clients, and actually this hard condition is actually 1/2. If you have strictly more than, if you have 1/2 or more, malicious clients, you know that you cannot have any guarantees on your learning. The Byzantine can take control of the learning. The malicious client can take control of the learning, which means that when you subsample, maybe you could be unlucky, and you subsample more malicious clients than clients that behave well, and basically you cannot have any guarantees on that. There are some new work actually that gives you some high probability results, and actually this is a paper that we will present next week at ICML that ensure you that with a well-established strategy of subsampling, you can still learn well. But I invite you to our presentation next week.
Okay, thanks. Yeah, I have one question, maybe just to clarify. So for this federated setting, so when you compute a batch, you just compute one batch, no, and you don't do multiple local steps. You just, so far the method works only for one.
So this is an interesting question. For now, it's just for one local step, indeed. Yeah. Actually, I started to think about it just after writing this paper, and if I remember well, I think you can still like with a small change or small modification of the algorithm still have some method that could work on that case. Okay, to be honest, it's been like 1 or 2 months that I thought about that, but I didn't work on it since. But I think there's an easy fix to have when you deal with several local steps. Now let's see.
Okay, thanks. Yeah, I think that would also be interesting to make it a bit more closer. Okay, perfect. Yeah, so there's so maybe 1 or 2 more questions. So there is one again from Satish in the chat. So based on your experience, could you help us to throw some light on how FBN can be helpful when the underlying data distribution changes in the client?
When the underlying distribution is?
It changes over time. So if the client data sets are
if the overall distribution, so each client could have indeed its distribution changing. This is something, but if the overall distribution, so the union of all the distribution is still the same, then there isn't any difference. But because what we do at each step is normalizing according to the global distribution. Now, if this global distribution changes too, I would say that, okay, and this is just a guess, I would say that you have to use actually this momentum parameter beta that would be somehow that would be proportional to how often this distribution change or how far one distribution is from the other. Meaning, how long do you want to remember your history from all distributions? I don't know if I answered your question.
Yeah, no, I think that explains a bit the intuition also behind beta and so on. That's good. So thanks. Yeah, is there one more live question maybe? No. Yeah, I think, okay, it was very good. So, there's one by Samuel.
Can I ask one quick? Just what I was wondering, whether you compared your FBN with this another popular approach of implementation of budget normalization in Federated learning, where actually each client just estimate its own running mean and variance, and this is never shared with central server. It goes more towards the personalization, but I think at least that was the kind of the implementation that I was aware of that somehow worked for Federated learning.
Yeah, actually, this was a question that we also asked to ourselves before. Actually, when we started this project, we said, okay, there is a problem with batch normalization, and people are trying to find another way to deal with normalization in general. And you can see a lot of normalization method that could be layer normalization or others, or even this one that you mentioned that is more like a personalization normalization. What we try to do here is, okay, we know that batch normalization is useful in centralized learning. Let's try to match it. And it was in that direction, in that research direction, that we tried to work and actually to also write the paper. And that's why we didn't directly compare ourselves to method that actually try to take another path to not use batch normalization as we know it. Now, it could be, I think, really interesting to see the differences. But here, the real objective of this paper was to say, okay, normalization as we know it, can be used in federated learning. But there are a lot of normalization methods. Layer normalization is one of the most known also in like LLMs or whatever. And yeah, we're not trying to let's say compare to those methods because they're doing completely different things, you know.
Yeah, makes sense. Thank you.
Good. Okay, so I think with this we can end this session. So thanks